The universe was once dark, dense, and almost perfectly simple. Before stars burned, before galaxies turned, before light could travel freely, gravity was already at work, quietly gathering matter into places where time itself would begin to slow. In that early silence, something immense was forming, not with violence at first, but with patience. If this calm journey through the universe brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these quiet explorations alive, and I hold that support with sincere thanks. Now, let's begin with the first truth. Part 1. What existed before the first black hole? Before black holes, before stars, before even atoms as we know them, the universe was filled with a smooth, cooling ocean of energy. Matter had not yet learned how to shine. It drifted silently, shaped only by the faint imprints left behind by the Big Bang itself. To understand the first black hole, we must begin in this era of near-uniform calm, when gravity was present, but had not yet found anything solid enough to collapse. If you could step into the universe at this time, there would be no light in any familiar sense, no stars, no planets, no glowing clouds. Space itself would feel dense and warm, filled everywhere with radiation and elementary particles moving in quiet, relentless motion. The universe was expanding, yes, but expansion did not yet mean emptiness. Everything was close together, pressed into a young cosmos still remembering its violent birth. In the first fractions of a second after the Big Bang, the universe was too hot and energetic for structure of any kind. Particles appeared and vanished in pairs. Forces we now know as separate, gravity, electromagnetism, the nuclear forces, were once unified. But as the universe expanded and cooled, this symmetry slowly broke. Space stretched, energy thinned, and time began to settle into a rhythm that allowed things to persist. As you breathe right now, you are surrounded by atoms that did not yet exist then. Back in this early epoch, protons and neutrons were only just forming. Electrons roamed freely, unable to bind to nuclei. Light itself could not travel far before being scattered again. The universe was opaque, more like a glowing fog than an open sky. This period is known as the radiation-dominated era. Radiation, not matter, controlled the behavior of the cosmos. Photons carried more energy than mass did, and gravity had little leverage. Even though gravity was already woven into spacetime, it was too weak compared to the pressure of radiation to pull matter together. Every attempt at collapse was gently pushed back outward. And yet, the universe was not perfectly smooth. Hidden within this apparent uniformity were tiny imperfections, minute differences in density left behind by quantum fluctuations during the universe's earliest moments. These fluctuations were unimaginably small, variations of 1 part in 100,000. But they mattered. They were the quiet fingerprints of chance, preserved and stretched across space as the universe expanded. You can think of these fluctuations as the universe's first memory. They were not structures yet, not objects, not even clouds. They were only tendencies, slight preferences for matter to gather here rather than there. Gravity noticed them even when nothing else could. As the universe cooled further, it entered the matter-dominated era. Matter finally outweighed radiation in its influence. Photons lost their grip, and gravity began to speak more clearly. This shift did not happen suddenly. It unfolded over hundreds of thousands of years, slowly tipping the balance. Eventually, about 380,000 years after the Big Bang, electrons combined with protons to form the first neutral hydrogen atoms. Light was finally free to travel long distances. The universe became transparent. This ancient light still surrounds you now as the cosmic microwave background, a faint afterglow cooled to just a few degrees above absolute zero. But even then, there were still no stars. The universe entered what scientists sometimes call the cosmic dark ages. Space was filled with neutral hydrogen gas and vast amounts of invisible dark matter. No sources of light had yet ignited. Darkness at this stage was not dramatic or ominous. It was simply patient. Dark matter played a crucial role during this time. Though it does not emit or absorb light, it carries mass, and mass means gravity. Dark matter began to clump first, forming vast halos that stretched across space like invisible wells. Ordinary matter, the kind that would one day form stars and planets, slowly fell into these wells. This falling was not fast. It took millions of years. Gravity works quietly, and in the early universe, it had to overcome the gentle pressure of warm gas and the momentum of expansion, but it never stopped pulling. Imagine standing perfectly still while the ground beneath you tilts by an amount so small you cannot feel it. Over time, that tilt becomes a slope. Over longer time still, it becomes a valley. Gravity worked like that, persistent, subtle, inevitable. Within these dark matter halos, gas began to collect. As it gathered, it slowly cooled. Cooling mattered because only cold gas can collapse further. Heat resists compression. Cold allows gravity to tighten its grip. At this stage, nothing remotely resembling a black hole existed. There were no dense cores, no collapsing stars, no singularities. Just enormous, diffuse clouds stretching across distances larger than entire galaxies today. But the conditions were quietly changing. As gas continued to fall inward, the densest regions grew slightly denser still. Pressure rose, temperatures climbed locally, even as the universe as a whole cooled. These regions were the ancestors of the first stars, though they had not yet crossed the threshold required to ignite. Gravity was learning where to concentrate its effort. One of the most important limitations at this time was the lack of heavy elements. Elements like carbon, oxygen, and iron, so essential to cooling gas efficiently, did not exist yet. The universe had only hydrogen, helium, and trace amounts of lithium. This meant gas clouds could not fragment easily into small pieces. When collapse finally began, it favored enormous structures. This detail matters deeply for the story of the first black hole. Because without efficient cooling, collapsing gas tended to form extremely massive objects. There was nothing to break the fall into smaller stars. Gravity gathered matter on a grand scale, preparing conditions that modern star formation no longer allows. As millions of years passed, the densest gas clouds continued to compress. The first stars were nearing birth. These stars would burn fiercely and briefly, setting the stage for the universe's first dramatic collapses. But at this moment, before the first black hole, everything was still suspended in anticipation. No horizons had formed, no regions of space-time had folded inward beyond return. Gravity had not yet crossed its critical threshold. The universe was balanced delicately between expansion and collapse, light and darkness, simplicity and structure. It is easy to imagine black holes as violent intrusions into the cosmos, but their story begins in stillness, in patience, in a universe that spent hundreds of millions of years quietly arranging matter into places where gravity could finally win. And as this slow gathering continued, one question began to take shape, faint but unavoidable. If gravity had all this time to work, what was the very first place where it finally succeeded? That question carries us gently forward into the moment when gravity found its first true foothold and the universe took its initial step toward darkness. Part 2. How did gravity find its first foothold? If gravity is everywhere, why doesn't everything collapse at once? In the early universe, gravity worked slowly, patiently amplifying the smallest imperfections. Tiny regions, just slightly denser than their surroundings, began to draw matter inward. These were not dramatic events. They were gentle preferences, invisible gradients that would, over millions of years, decide where the universe's first monsters would emerge. Gravity is the weakest of the fundamental forces, yet it is the most patient. It does not rush, it does not overpower. Instead, it accumulates influence over time, shaping the universe through persistence rather than strength. In the early cosmos, this patience mattered more than anything else. To understand why gravity did not immediately collapse the universe into a single object, you must imagine the universe not as static space, but as space itself stretching. Expansion was the dominant motion. Every region was moving away from every other region, carried outward by the momentum of the Big Bang. Gravity had to work against this expansion, and in the beginning, it barely could. Even as you lie still now, you are moving with Earth, with the solar system, with the galaxy. Motion feels like rest when everything moves together. The early universe was similar. Expansion was smooth, uniform, and nearly identical everywhere. Gravity needed differences to act upon, and at first, those differences were barely there. But barely was enough. The tiny density variations imprinted during the universe's earliest moments acted like seeds. Where matter was just a fraction more concentrated, gravity pulled slightly harder. That extra pull drew in more matter, increasing density further. This feedback loop was slow, almost imperceptible, but relentless. Physicists call this process gravitational instability. It is the quiet mechanism by which structure forms. Nothing collapses suddenly. Instead, regions that are already denser grow denser still, while emptier regions become emptier. Over time, contrast emerges from uniformity. You can think of it like a perfectly calm lake with a barely noticeable dip in the surface. Water does not rush toward it, but given enough time, currents shift. The dip deepens. Eventually, the lake is no longer flat. Gravity works in much the same way, sculpting the universe through accumulated imbalance. One of the most important players in this process was dark matter. Unlike ordinary matter, dark matter does not interact with light or radiation. This made it immune to many of the pressures that resisted collapse in the early universe. While radiation pushed ordinary matter outward, dark matter felt only gravity. Because of this, dark matter began clumping first. Long before gas clouds condensed, dark matter formed vast invisible halos. These halos were not solid objects. They were diffuse, ghostly concentrations spread across enormous volumes of space. Yet their gravitational pull was real, and it shaped everything that followed. As dark matter halos grew, they created gravitational wells, regions where space-time curved just enough to slow the expansion locally. Ordinary matter drifting through space began to feel these wells and gradually fell inward. Not falling like an object dropped from a height, but drifting, slowly surrendering its outward momentum. This inward motion took millions of years. Gravity does not hurry, especially when working on cosmic scales, but it never stops pulling. Within these wells, gas density increased. As density increased, collisions between particles became more frequent. Energy was exchanged. Some energy escaped as radiation, allowing the gas to cool. Cooling was essential. Without it, pressure would halt further collapse. Yet cooling in the early universe was inefficient. The gas consisted almost entirely of hydrogen and helium. Heavier elements, which today help gas radiate energy and cool quickly, did not yet exist. This meant that collapsing regions remained warm, resisting fragmentation. Gravity had to overcome not just expansion, but heat. This resistance slowed collapse further, but it also shaped what would eventually form. Instead of breaking into many small structures, gas tended to collapse into fewer, much larger ones. Gravity, when finally successful, would succeed on a grand scale. Another factor quietly influencing gravity's foothold was sound. In the early universe, pressure waves, called baryon acoustic oscillations, rippled through the hot plasma of matter and radiation. These waves set characteristic scales for structure formation, subtly guiding where matter could collect and where it could not. Even after the universe cooled and became transparent, the imprint of these waves remained, shaping the large-scale distribution of matter. So gravity did not act alone. It worked within constraints set by expansion, radiation, sound, and composition. Its success required a precise alignment of conditions. Over time, as the universe expanded further, matter thinned out overall, but within dark matter halos, density continued to rise. Eventually, some regions crossed a critical threshold. Gravity became strong enough locally to dominate over pressure and expansion. This moment was gravity's first true foothold. It did not announce itself with light or violence. No explosion marked the occasion. It was simply the point at which inward motion no longer reversed. Collapse, once begun past this threshold, could continue. In these regions, gas began to contract more decisively. Temperatures rose at the center, pressure increased. The balance between gravity and resistance became delicate, but gravity now had the advantage. It is important to understand that this foothold did not immediately produce black holes. It produced the conditions that would eventually allow them. The first outcome of gravity's success was the formation of the universe's first stars. But those stars would be unlike anything we see today. Because gravity's foothold formed in an environment with inefficient cooling and enormous available mass, the first stars were destined to be massive, extremely massive. Their birth was a direct consequence of how gravity first learned to win. As gas continued to fall inward, rotation began to matter. Even tiny amounts of angular momentum, small sideways motions present from the beginning, were amplified during collapse. Spinning disks formed, matter flattened, gravity funneled material toward dense centers, while excess angular momentum spread outward. This rotation did not prevent collapse, but it shaped it, concentrating mass into cores that would soon ignite nuclear fusion. Gravity had found its method. It worked through imbalance, patience, and accumulation. It did not overpower the universe. It waited for the universe to give it permission. And once gravity gained this foothold, it never truly lost it. Every structure you see today, galaxies, stars, planets, black holes, traces its lineage back to this quiet victory. Even now, gravity continues the same process. It amplifies differences. It gathers matter. It shapes time and space without urgency or sound. The first foothold was not dramatic, but it was decisive. Because once gravity proved it could overcome expansion in even a single region, the universe's future was set. Collapse would repeat, structures would multiply, and somewhere within these growing concentrations, gravity would push matter past every known limit. As this gentle process continued, another question began to emerge, slowly and inevitably. If gravity could gather matter into these first dense regions, what kinds of structures would appear first? That question carries us forward into the birth of the universe's earliest forms, the first structures to ever exist, rising quietly from the patient pull of gravity. Part 3. What were the first structures to ever form? Long before galaxies had names or shapes, the universe organized itself into vast, invisible webs. Filaments of dark matter stretched across space, guiding ordinary matter into knots and intersections. These were the scaffolds of creation, quiet frameworks where gas could cool, gather, and eventually ignite. The first black hole was born within one of these ancient crossroads. If you could drift through the universe at this stage, you would not see stars or glowing spirals. You would see nothing at all. Yet beneath that darkness, structure was already taking form, not through light, but through gravity. The universe was learning how to arrange itself. Dark matter was the first architect. Though invisible, it outweighed ordinary matter by more than 5 to 1. It moved differently too. While ordinary matter felt pressure from radiation and heat, dark matter felt only gravity. That freedom allowed it to collapse earlier, tracing out the universe's first large-scale patterns. Over millions of years, dark matter gathered into elongated filaments, sheets, and dense nodes. Together, they formed what cosmologists call the cosmic web. This web spanned enormous distances, far larger than any galaxy. It was not rigid or solid. It was a statistical structure, defined by probability and mass rather than edges or surfaces. Ordinary matter followed this invisible map. Hydrogen and helium gas drifted gently toward the filaments, pulled inward by gravity's steady hand. Where filaments intersected, gravity was strongest. These intersections became gathering points, regions where gas density slowly increased over time. Nothing moved quickly. Collapse was not a fall, but a surrender. As gas accumulated, it began to cool. Cooling was slow because the early universe lacked heavy elements that radiate energy efficiently. But even inefficient cooling, given enough time, makes a difference. As gas lost energy, pressure weakened. Gravity tightened its grip. These growing concentrations of gas were the universe's first structures, not stars, not galaxies, but protostructures. They had no sharp boundaries. They were defined only by gradual changes in density, by regions where matter preferred to linger. Within these regions, gravity and motion began to compete in more complex ways. Gas did not fall straight inward. It carried small amounts of angular momentum inherited from the universe's earliest fluctuations. As collapse continued, this rotation became more important, flattening gas into slow-spinning disks and streams. This motion was not chaotic. It followed clear physical laws. Conservation of angular momentum ensured that as matter moved inward, it spun faster. Gravity concentrated mass, rotation redistributed it. Together, they shaped the earliest cosmic forms. At the centers of the densest knots, gas clouds grew massive, extremely massive. Without heavy elements to fragment the clouds into smaller pieces, collapse favored scale. These clouds did not break apart easily. Instead, they funneled enormous amounts of mass toward single central regions. These regions would soon give birth to the first stars. But before ignition, there was a long period of compression. Gas grew denser, temperatures rose, pressure increased. The balance between gravity pulling inward and heat pushing outward became increasingly delicate. This balance is fundamental to astrophysics. Every star, every planet, every black hole exists because of how this balance resolves. In the early universe, the resolution favored extremes. When the first stars finally ignited, they were unlike anything that would come later. They were composed almost entirely of hydrogen and helium. Astronomers call them population 3 stars. They were massive, hot, and short-lived, often hundreds of times more massive than our Sun. These stars formed almost exclusively at the nodes of the cosmic web, where dark matter halos were largest and gas supply was abundant. Gravity had built these places carefully over hundreds of millions of years, preparing them for sudden brilliance. When nuclear fusion began in their cores, it marked the first time the universe produced light on its own. Starlight pierced the cosmic darkness for the first time. Ultraviolet radiation flooded surrounding space, beginning the long process of rionizing the universe. But this light came at a cost. The same mass that allowed these stars to ignite also sealed their fate. Massive stars burn their fuel quickly. Their cores grow heavier with each fusion reaction, building elements up to iron. Iron cannot release energy through fusion. When it accumulates, the balance fails. For the first stars, this failure was often absolute. In many cases, gravity overwhelmed all remaining resistance. The core collapsed inward with such force that not even explosive shock waves could halt it. Matter fell inward faster than light could escape. Space and time curved inward beyond return. This was the birth of the first black holes. But the black hole was not the beginning of structure. It was the consequence of it. It emerged only because gravity had already succeeded in building something large, dense, and fragile enough to collapse completely. Some of the earliest black holes formed directly from these massive stars. Others may have formed even more quietly, through the direct collapse of gas clouds that never became stars at all. In the densest regions of the cosmic web, gas may have flowed inward so efficiently that nuclear fusion never ignited. Collapse proceeded uninterrupted, straight into darkness. In either case, location mattered. The first black holes did not appear randomly. They formed at the deepest gravitational wells, at the intersections of filaments where matter had been gathering since the universe's youth. These places had the richest supply of fuel and the strongest gravitational fields. Once formed, these black holes did not remain isolated. Surrounded by dense gas and embedded within growing dark matter halos, they began to feed. Matter spiraled inward, heating and glowing briefly before vanishing beyond the event horizon. Each feeding episode increased the black hole's mass, deepening its gravitational influence. At the same time, the energy released during accretion affected the surrounding environment. Radiation heated nearby gas, sometimes slowing further inflow. In this way, black holes began shaping their surroundings almost as soon as they were born. This feedback loop, gravity gathering matter, matter feeding black holes influencing their environment, became a defining feature of cosmic evolution. Over time, the structures that hosted these early black holes grew larger. Dark matter halos merged, gas streams combined, small protogalaxies formed, still irregular and chaotic, but unmistakably structured. The cosmic web continued to evolve, stretching and thickening as the universe expanded. Filaments fed galaxies. Galaxies fed black holes. Patterns established in the universe's first billion years would persist for the next 13. Even now, when astronomers observe the large-scale distribution of galaxies, they see the same web-like structure predicted by dark matter models. The scaffolding remains. The universe remembers its earliest design. The first structures were not luminous. They were gravitational. They did not announce themselves with light, but with motion. They taught gravity where to work and how to persist. And somewhere within these ancient frameworks, gravity crossed a final threshold. It gathered enough mass, concentrated it tightly enough, and bent space-time deeply enough to create something entirely new. Not just a star, not just a structure, but a boundary beyond which return was impossible. As we continue this quiet journey, one question naturally follows. If these first structures created stars massive enough to collapse completely, what made those earliest stars so different from the ones that shine today? That question leads us gently onward into the strange and powerful nature of the universe's first stars. Part 4. Why were the first stars so different from today's stars? The earliest stars were nothing like the ones that warm the night sky now. They were enormous, unstable, and short-lived, composed almost entirely of hydrogen and helium. Without heavier elements to regulate their behavior, they burned fast and hot, pushing gravity and nuclear fire into a delicate but doomed balance. These stars lived quickly, and in doing so, prepared the conditions for something far darker. To understand why the first stars were so extreme, you have to let go of everything familiar about starlight. The stars you know are shaped by generations of cosmic recycling. They form from gas enriched with heavy elements forged in earlier stellar deaths. The first stars had no such inheritance. They were born into a chemically simple universe. In the early cosmos, hydrogen and helium dominated almost completely. These light elements behaved differently than the complex mixtures found in modern star-forming regions. They were inefficient at cooling. When gas cannot cool easily, it resists breaking apart. Instead of fragmenting into many small stars, it collapses into fewer, much larger ones. Gravity, once again, favored scale. As gas clouds collapsed within the deepest gravitational wells of the cosmic web, they accumulated enormous mass before ignition. Temperatures rose steadily at their centers. Pressure increased. Eventually, nuclear fusion began, converting hydrogen into helium and releasing vast amounts of energy. But this ignition did not bring stability. In modern stars, elements like carbon, oxygen, and nitrogen help regulate fusion through well-understood cycles. These elements act like valves, smoothing energy release and allowing stars to settle into long, steady lifetimes. The first stars lacked these controls. Fusion proceeded in a more direct, violent way. As a result, the first stars shone intensely. They burned at surface temperatures far hotter than most stars today, emitting enormous amounts of ultraviolet radiation. Their light was not gentle, it was harsh, energetic, and transformative. This radiation ionized surrounding hydrogen, stripping electrons from atoms and altering the chemistry of the universe itself. Yet, even as they blazed, these stars were unstable. Their immense mass meant gravity crushed their cores with extraordinary force. At the same time, radiation pressure pushed outward, attempting to tear the star apart. The balance between these forces was precarious. Small changes could tip it one way or the other. For some of the most massive first stars, this balance failed spectacularly. As fusion progressed, heavier elements built up in their cores. Each new fusion stage burned faster than the last. Hydrogen fusion lasted millions of years, helium fusion only hundreds of thousands. Later stages, if they occurred at all, lasted mere years or days. Time for these stars moved quickly. Eventually, iron accumulated in the core. Iron fusion consumes energy instead of releasing it. At that moment, the star's central engine stalled. Gravity, no longer opposed by outward energy flow, surged inward. In modern stars, this collapse often triggers a supernova, an explosive rebound that scatters material into space. But for many first-generation stars, gravity was simply too strong. The core collapsed faster than any explosion could reverse. The star did not die in a blast of light. It vanished inward. This quiet collapse marked the birth of the universe's first black holes. But not all first stars met this fate in the same way. Some, in a narrow mass range, likely exploded as pair instability supernovae, completely tearing themselves apart and leaving no remnant behind. These explosions enriched surrounding space with the first heavy elements, seeding future generations of stars. Others collapsed directly, forming black holes with tens or even hundreds of times the mass of the Sun. What determined the outcome was mass. Mass governed everything. It dictated how fast fusion burned, how strong gravity became, and whether collapse could be halted. In the early universe, mass was abundant and unchecked. The environments that formed these stars did little to limit their growth. Gas streams fed them continuously. Radiation, though intense, struggled to escape dense inflows. Accretion continued even after ignition, pushing stellar masses ever higher. These conditions no longer exist today. As the universe aged, heavy elements accumulated. Cooling became more efficient. Gas clouds fragmented more easily. Star formation shifted towards smaller, longer-lived stars like the Sun. The era of cosmic giants ended, but its legacy remained. The first stars changed the universe in profound ways. Their radiation rionized space, ending the cosmic dark ages. Their deaths enriched gas with metals, and their collapses introduced black holes into the cosmic landscape. In many ways, black holes are the fossils of these ancient stars. They carry the memory of an era when gravity and simplicity combined to produce extremes. Every black hole formed from a first-generation star is a record of that time, preserved not in light, but in mass and curvature. As you rest now, consider how different the night sky would look if the universe had begun with stars like the Sun. There would be fewer black holes. Galaxies would grow differently. Even time itself, shaped by gravity, would unfold along altered paths. The universe we inhabit was forged by these early excesses. The first stars did not aim to be stable. They existed to burn, to collapse, and to transform. Their brief lives accelerated cosmic evolution, compressing millions of years of change into moments of brilliance and collapse. And through their collapse, they created the first places where gravity completely won. As we drift onward, one question naturally follows from this fiery beginning. If the first stars were so massive, just how large could they grow before gravity took full control? That question carries us gently into the next chapter, where we explore the true scale of the universe's first giants and how their size sealed their fate. Part 5. How massive did the first stars really become? Some of the universe's first stars grew to hundreds of times the mass of our Sun. Their gravity crushed their cores with relentless pressure, while radiation fought desperately to escape. As you imagine their size, it helps to remember that mass is not just weight, it is gravity's voice. And in these stars, gravity spoke louder than it ever had before. When astronomers talk about stellar mass, they are not just describing how much material a star contains. They are describing its destiny. Mass determines how a star forms, how it shines, how long it lives, and how it dies. For the first stars, mass was not a gentle parameter, it was overwhelming. In the modern universe, most stars form with masses comparable to or smaller than the Sun. This is not an accident, it is the result of efficient cooling, turbulence, magnetic fields, and feedback from nearby stars. These processes break collapsing gas clouds into many small fragments. Each fragment becomes a modest star. The early universe had none of these safeguards. Gas clouds composed only of hydrogen and helium could not cool efficiently. Without heavy elements, the gas stayed warm as it collapsed. Warm gas resists fragmentation. Instead of shattering into hundreds of small pieces, it tended to remain whole, funneling enormous amounts of mass toward a single growing core. Gravity encouraged this concentration. As gas flowed inward along the filaments of the cosmic web, it fed forming stars continuously. Accretion did not stop when fusion ignited. In many cases, it accelerated. Dense streams of gas poured onto the young star, adding mass faster than radiation could push it away. Imagine a fire fed not by scattered sparks, but by a steady river of fuel. That was the situation for the first stars. Simulations of early star formation suggest that many of these stars reached masses of 100 to 300 times that of the Sun. Some may have grown even larger, approaching 1,000 solar masses under the right conditions. At these scales, stars behave very differently. Gravity at the core became extreme. Pressure and temperature soared far beyond what we see in typical stars today. Fusion reactions proceeded at furious rates. Radiation pressure, light itself pushing outward, became one of the primary forces opposing collapse. For a time, balance held. This balance, called hydrostatic equilibrium, is what defines a star. Gravity pulls inward, pressure from fusion pushes outward. In the first stars, this equilibrium existed on a knife's edge. Any shift in mass, temperature, or fusion rate could destabilize the entire structure. And instability was common. Because these stars were so massive, their internal layers were turbulent. Convection churned material from core to surface. Fusion products mixed rapidly. There was little separation between stages of burning. The stars evolved quickly, racing through their fuel in just a few million years. To put this in perspective, the Sun will shine for about 10 billion years. Many first stars burned out in less than 5 million. Some lived only a few 100,000 years. Time for them was compressed. As mass increased, so did the star's influence on its surroundings. Intense ultraviolet radiation flooded nearby space, heating and ionizing gas. This radiation could eventually limit further accretion by pushing gas away. But for the most massive stars, gravity often won this struggle as well. Their gravitational pull was simply too strong. The question of how massive the first stars could become is still an active area of research. Astronomers cannot observe these stars directly. They are long gone. Instead, scientists rely on computer simulations grounded in physics and constrained by observations of the early universe. What these simulations reveal is not a single number but a range of possibilities. Some stars likely stalled at around 50 solar masses, others surged past 100. In rare environments, especially in the densest regions of the cosmic web, stars may have grown far beyond that, entering regimes where they were barely stars at all. At extreme masses, new physical effects emerged. Radiation pressure became so intense that it could destabilize the star internally. Electron-positron pairs formed in the core, reducing pressure support and triggering rapid collapse or explosive instability. This process, known as pair instability, could either partially disrupt the star or destroy it completely. For stars above a certain mass threshold, even this instability was not enough to save them. Gravity overwhelmed every resisting force. When collapse began in these giants, it was swift and total. The core fell inward at a significant fraction of the speed of light. Temperatures spiked. Densities became unimaginable. In some cases, there was no supernova, no outward shock strong enough to reverse the collapse. The star crossed a point of no return. This is why the mass of the first stars matters so deeply to the story of black holes. A star of 10 solar masses might explode and leave behind a neutron star. A star of 50 solar masses might form a black hole. But a star of several hundred solar masses collapses in a fundamentally different way. Its gravity dominates not just the star, but space-time itself. The black holes formed from these massive stars were already substantial at birth. Tens or hundreds of solar masses created in a universe dense with fuel. They were not small seeds struggling to grow, they were heavy from the beginning. This initial mass advantage helped explain a long-standing cosmic mystery. When astronomers observe the early universe, they find quasars, brilliant beacons, powered by supermassive black holes existing less than 1 billion years after the Big Bang. For decades, scientists wondered how black holes could grow so large so quickly. The answer likely begins here. If the first stars were extraordinarily massive, the black holes they left behind would have had a significant head start. Combined with rapid accretion in dense early environments, this made the growth of supermassive black holes possible within cosmic time limits. Mass, in this context, is momentum across time. The first stars did not merely shine, They shaped the trajectory of cosmic evolution. Their size dictated how gravity would behave in the densest regions of the universe. Their collapse carved the first deep wells in space-time. As you rest now, it may feel strange to think of stars as temporary, fragile things. But the universe has always favored impermanence. It builds quickly, tests structures brutally, and preserves only what can survive under extreme conditions. The first stars were a test. They explored the upper limits of what a star could be. They pushed gravity, fusion, and radiation to their extremes. And when they failed, they did so in a way that reshaped the cosmos. Their immense mass was not wasted. It was transformed. It became black holes, curvature, and influence. It became the silent centers around which galaxies would one day gather. It became the reason gravity would never again be a quiet background force. As we move gently forward, one question remains, heavy and unavoidable. If stars of such mass collapsed under their own gravity, what exactly happened at the moment when support finally failed? That question leads us deeper still, into the instant when collapse becomes inevitable and gravity takes full control. Part 6. What happens when a star can no longer support itself? At a certain point, nuclear fusion can no longer resist gravity's inward pull. When that balance fails, collapse becomes inevitable. For the first massive stars, this collapse did not always end in an explosion. Sometimes there was no outward resistance strong enough to stop the fall. Matter folded inward, faster and faster, until space itself gave way. Every star lives inside a quiet negotiation. Gravity presses inward, trying to compress the star into something smaller and denser. Nuclear fusion pushes outward, releasing energy that holds the star up against that pressure. As long as these two forces remain balanced, the star endures. When the balance breaks, the star's fate is sealed. For much of a star's life, fusion provides reliable support. Hydrogen fuses into helium, releasing energy that travels outward as radiation and heat. This energy creates pressure, and that pressure counteracts gravity. In stable stars, this balance can last for billions of years. But fusion is not endless. Fuel is finite, and in massive stars, it is consumed rapidly. As hydrogen becomes scarce in the core, fusion slows. Gravity responds immediately. The core begins to contract, squeezing inward and heating up. This rise in temperature ignites the next stage of fusion, helium into heavier elements. For a time, the balance is restored, but each new fusion stage is shorter than the last. Helium burning lasts far less time than hydrogen burning. Carbon fusion lasts even less. Oxygen, neon, silicon. Each stage flashes by more quickly, each producing less outward support. The star becomes layered like an onion, with heavier elements toward the center and lighter ones above. These layers burn simultaneously, each contributing briefly to the struggle against gravity. Eventually, the core becomes iron. Iron is different. Fusing iron does not release energy, it consumes it. At the moment iron dominates the core, the star loses its last effective source of pressure. Fusion no longer helps. Gravity, which has been waiting patiently, finally takes over completely. Collapse begins almost instantly. The core contracts at incredible speed, shrinking from thousands of kilometers across to tens in less than a second. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. Matter becomes incomprehensibly dense. In many stars, this collapse triggers a rebound. The collapsing core stiffens suddenly when neutron pressure halts further compression. Shock waves form, energy surges outward. A supernova explosion tears the star apart, scattering heavy elements into space and leaving behind a neutron star or a small black hole. But for the first massive stars, this rebound often failed. Their cores were simply too massive. Gravity was too strong. Neutron pressure could not stop the collapse. Shockwaves stalled. Energy was swallowed before it could escape. Instead of exploding outward, the star continued collapsing inward. This is a crucial distinction. An explosion requires resistance. It requires something to push back. In these early giants, there was nothing left that could. Gravity dominated every scale of the star's interior. As collapse continued, matter fell inward faster and faster. Temperatures rose beyond trillions of degrees. Densities surpassed anything found in atomic nuclei. The familiar laws of physics began to strain under the conditions. Space-time itself responded. According to Einstein's theory of general relativity, mass and energy tell space-time how to curve. In these collapsing cores, mass was being compressed into ever smaller volumes. The curvature deepened rapidly. At a certain point, the escape velocity from the collapsing region exceeded the speed of light. That point is not marked by light or sound, it is defined by geometry. Once reached, no signal from within can ever reach the outside universe again. An event horizon formed. This moment is the true birth of a black hole. From the outside, collapse appears to slow as matter approaches the horizon. Time stretches, light redshifts. The infalling material seems to fade away. But from its own perspective, collapse continues uninterrupted. Matter crosses the horizon in finite time and continues inward toward a singularity, a region where density and curvature become extreme beyond our current ability to describe. The star is gone. What remains is not an object in the traditional sense, but a region of space-time defined by mass, spin, and charge. Its surface is not solid, its boundary is not material. It is simply the point beyond which return is impossible. For the first stars, this transition could happen quietly. No brilliant supernova marked the end. No heavy elements were scattered. The universe did not see the collapse. It only felt the change in gravity. This silence is important. It means that many of the universe's first black holes formed without announcing themselves. They emerged in darkness, hidden within dense clouds of gas and dark matter, already embedded in the deepest gravitational wells of the cosmic web. Once formed, the black hole did not stop influencing its surroundings. Even without light, its gravity continued to shape nearby matter. Gas fell inward, accretion disks formed, friction heated the infalling material, allowing energy to escape before crossing the horizon. The black hole began to glow indirectly, not from within, but from the struggle of matter trying to fall in. This glow could be intense. In some cases, accretion produced jets of energy that blasted outward along the black hole's poles, influencing regions far beyond the original star. Even the earliest black holes may have begun shaping their environments this way, but at the moment of collapse itself, there was no spectacle, just inward motion. It is tempting to imagine collapse as violent, chaotic, explosive, but the formation of a black hole is, in many ways, the opposite. It is order asserting itself completely, gravity reaching its most efficient expression. Every path points inward, every future leads deeper. The star does not resist, it cannot. The rules have changed. This is why black holes are such profound objects. They are not just remnants of stars, they are places where the structure of space-time itself reorganizes around mass. For the first stars, collapse was not an accident. It was the natural conclusion of their immense size and brief lives. Their mass made stability impossible. Their simplicity removed safety valves. Their gravity was always destined to win. As you breathe now, supported effortlessly by Earth beneath you, it may feel strange to imagine matter collapsing without limit. But gravity never forgets. It remembers every bit of mass, every density fluctuation, every imbalance. Given enough time and the right conditions, it will always find a way inward. The first black holes were not mistakes. They were solutions. Solutions to the problem of what happens when mass accumulates beyond the ability of any force to resist it. And once the universe found this solution, it would use it again and again. As we continue this quiet journey, one question naturally arises from this moment of collapse. When does collapse truly become irreversible? When does a dying star cross the line beyond which nothing can escape? That question carries us gently forward toward the boundary itself, the event horizon, and the precise moment when a collapsing star becomes something entirely new. Part 7. When does collapse become a black hole? A black hole is not created when matter simply becomes dense. It forms when escape becomes impossible. As the collapsing core shrank, Gravity curved spacetime so severely that even light could no longer find a path outward. This boundary, the event horizon, marked the quiet birth of the universe's first true abyss. It is tempting to imagine a black hole as an object, something solid, something formed at a specific moment like a planet or a star. But a black hole is not defined by what it is made of. It is defined by what space-time itself has become around it. To understand when collapse becomes a black hole, you have to shift your perspective. The crucial change is not in the matter, but in geometry. As a massive star collapses, its core shrinks steadily. Density rises, gravity strengthens, but none of this alone creates a black hole. Stars can become incredibly dense without crossing that line. White dwarfs and neutron stars are proof of this. They are extreme, compact objects where matter is crushed into unfamiliar states, yet light can still escape. The defining threshold is escape velocity. Every object in the universe has one. It is the speed required to break free from its gravitational pull. For Earth, it is about 11 kilometers per second. For the Sun, over 600 kilometers per second. As an object becomes more massive or more compact, its escape velocity increases. In a collapsing stellar core, escape velocity rises rapidly. At first, particles must move faster to escape. Then, photons, light itself, begin to struggle. Light always travels at the same speed, but gravity does not slow light down in the usual sense. Instead, it bends. The space light must travel through. Paths curve, time stretches, directions tilt inward. As collapse continues, there comes a moment when the escape velocity reaches the speed of light. That moment defines the event horizon. Once this boundary forms, escape is no longer possible, not because matter or light lacks energy, but because all possible paths forward lead inward. Space-time itself has tilted so completely toward the center that outward directions no longer exist. This is not a surface you could touch. It is not a shell of matter. It is a geometric boundary written into space-time. From far away, the formation of this boundary looks strange. As matter approaches the event horizon, it appears to slow down. Light emitted from it becomes increasingly redshifted, stretched to longer and longer wavelengths. To a distant observer, the collapsing star seems to freeze, fading gradually into darkness. But this is an A-bomb illusion of perspective. From the point of view of the infalling matter, nothing special happens at the horizon itself. There is no sudden jolt, no shock, no barrier. Collapse continues smoothly. Time proceeds normally. The horizon is crossed in finite time. This difference in perspective is not philosophical. It is a direct consequence of how time behaves in strong gravitational fields. Near a forming black hole, time slows relative to distant observers. This time, dilation becomes extreme at the horizon. From the outside, collapse never quite finishes. From the inside, it does. This is why black holes feel so counterintuitive. They are not objects sitting in space. They are regions where time and space exchange roles. Inside the event horizon, inward is no longer a direction. It is a destiny. Every future path leads deeper toward the center. Just as you cannot move backward in time, nothing inside the horizon can avoid moving inward. The singularity is not a place you fall toward. It is a moment in your future. For the first black holes, this transition likely happened without fireworks. The collapse was swift. The mass was enormous. The horizon formed quickly and quietly. No explosion announced it. No light escaped to mark the moment. The universe simply acquired a new region from which information could no longer return. This quiet birth is important. It means the first black holes did not dramatically disrupt their surroundings at the instant of formation. Their influence grew afterward, through accretion and gravitational interaction, not through a sudden blast. Once the horizon existed, the black hole was complete in a fundamental sense. Nothing added afterward could change that basic fact. Matter could fall in, increasing the black hole's mass and size, but the defining boundary was already there. The size of this boundary depended only on mass. For a non-rotating black hole, the radius of the event horizon, called the Schwarzschild radius, is directly proportional to its mass. Double the mass, double the radius. For a black hole with the mass of the Sun, this radius is about 3 kilometers. For a black hole hundreds of times more massive, The horizon spans hundreds of kilometers. This means something quietly surprising. The more massive a black hole is, the gentler the curvature of space-time at its horizon. For the first massive black holes, crossing the horizon would not necessarily involve extreme tidal forces. Spaghettification, the stretching effect often dramatized, becomes severe only much deeper inside. In other words, the most extreme black holes are not violent at the boundary. They are smooth. This smoothness makes their formation even more subtle. Nothing in local physics signals the exact moment when a horizon forms. Only the global structure of space-time reveals it. For the universe, this was a new kind of object. A black hole is the only place where gravity completely defeats every other force. Electromagnetism, nuclear forces, pressure, radiation, all become irrelevant beyond the horizon. Gravity is no longer resisted, it defines everything. Once the first black hole formed, the universe had crossed a conceptual threshold. There now existed regions where cause and effect were permanently cut off from the rest of space-time. Regions where information could be lost from the observable universe. Regions where time itself pointed inexorably inward. This raised deep questions physicists still wrestle with today. What happens to information that falls in? Does it vanish, or is it preserved in some hidden form? Is the singularity real, or a sign that our theories break down? How does quantum mechanics coexist with horizons? The first black holes did not answer these questions, they posed them. And yet, despite their mystery, black holes are remarkably simple from the outside. Once formed, a black hole can be fully described by just a few properties: mass, spin, and electric charge. Everything else, the details of what fell in, is erased from view. This simplicity is deceptive. It hides an interior we cannot see and perhaps cannot fully understand. It hides physics at the edge of our knowledge, and it began, quietly, with the collapse of the first massive stars. As you lie still now, surrounded by a universe that feels solid and predictable, it is worth remembering that reality contains places where prediction fails, where futures converge, where escape is not an option. The first black hole marked the universe's entry into that regime. It was not loud, it was not dramatic, it was inevitable. And once that boundary formed for the first time, it would form again and again, shaping galaxies, guiding growth, and anchoring some of the largest structures in existence. As we drift onward, one question naturally follows. If the first black holes formed this way, quietly and early, how large were they at birth, and how did their size compare to the monsters we see today? That question carries us gently forward into the scale of the universe's first black holes and the surprising story of how something small could become unimaginably vast. Part 8. Why didn't the first black hole explode? Modern supernovas scatter elements across space, but the first black holes often formed in near silence. Their stars were so massive that collapse outpaced explosion. Instead of a brilliant outward blast, gravity won completely, sealing the star's fate in darkness. The universe did not witness these births with light, only with absence. To understand why the first black holes did not explode, it helps to reconsider what an explosion actually is. A supernova is not simply collapse. It is collapse followed by resistance. It is gravity pulling inward, meeting something strong enough to push back, and releasing that struggle outward in a final burst of energy. The first massive stars often lack that resistance. In many modern stars, when the core collapses, it reaches a state where matter becomes incredibly stiff. Neutron pressure halts the inward fall. The core rebounds. A shockwave forms and travels outward, tearing the star apart. This rebound, aided by neutrinos and complex plasma physics, is what produces a supernova. But this outcome depends on a delicate balance of mass, pressure, and energy flow. For the first stars, that balance was often broken before it could form. Their cores were simply too heavy. When collapse began, it accelerated so rapidly that no stable neutron core could form in time. Gravity crushed the core past every known pressure barrier before a rebound could develop. The inward fall became unstoppable. In these stars, collapse was not followed by explosion. It replaced it. Another key factor was energy loss. As the core collapsed, it released enormous numbers of neutrinos, nearly massless particles that carry energy away almost effortlessly. In less massive stars, neutrinos can deposit enough energy in the outer layers to help revive a stalled shockwave. But in the most massive early stars, neutrinos escape too easily and too quickly. Energy leaked away before it could do any work. Without that energy, the outer layers of the star never received the push needed to escape gravity. They continued falling inward, feeding the collapse rather than resisting it. Time also played a role. The collapse of a massive stellar core happens on timescales measured in milliseconds. In the most extreme stars, this timescale was even shorter. There was simply not enough time for complex processes to unfold. Gravity did not pause, it rushed. An explosion requires coordination. It requires pressure waves to build, reflect, and amplify. It requires delays. The first black hole-forming collapses allowed none of that. They were too fast, too heavy, too decisive. The universe had learned how to collapse more efficiently than it had learned how to explode. There is also the question of rotation. Many early stars likely rotated rapidly, fed by streams of gas flowing along the filaments of the cosmic web. Rotation can support a star against collapse to some extent, but it can also complicate explosion mechanisms. Rapid rotation can funnel matter inward along preferred paths, focusing collapse rather than diffusing it. In some cases, rotation may have helped launch narrow jets, but even these jets were often swallowed before they could escape the infouling material. The star collapsed faster than any jet could carve a path outward. So instead of a spherical explosion, collapse became asymmetric, inward-focused, and silent. From the outside, the star's disappearance would have been subtle. There would be no sudden flash visible across the universe. The light of the star might dim, redden, and fade as collapse progressed. Eventually, it would vanish entirely, replaced by a gravitational presence with no surface and no light. This is why the first black holes left no immediate chemical signature. Supernovae enrich the universe by scattering heavy elements, carbon, oxygen, iron, into space. These elements become the building blocks of future stars, planets, and life. Silent collapses do not perform this service. They lock their material away behind an event horizon. As a result, the earliest black holes did not contribute directly to chemical enrichment. That task fell to a subset of first stars that exploded completely or partially, seeding the universe with metals. The silent black hole births shaped the universe differently. Instead of spreading material outward, they concentrated mass inward. They created gravitational sinks that would later influence the growth of galaxies and the motion of gas on large scales. In this sense, explosions and silent collapses played complementary roles. One spread matter, the other gathered it. There is a deeper reason why silence was favored early on. The early universe was dense. Gas filled space more uniformly than it does today. Even if an explosion had occurred, much of its energy would have been absorbed locally. Shockwaves would have been damped quickly. Radiation would have been scattered and trapped. Light struggled to travel freely in this environment, so even when explosions did occur, their visibility was limited. The universe was not yet transparent in the way it is now. Darkness absorbed violence. But for the most massive stars, even this limited visibility never came. Collapse completed before outward energy could form. The result was a universe that gained black holes quietly, without dramatic punctuation. This quietness is one reason black holes are so difficult to study observationally. They do not announce themselves at birth. They reveal themselves later, through interaction, through accretion, through motion, through the bending of light and time around them. The first black holes likely spent long periods growing invisibly, embedded in dense gas clouds, slowly increasing their mass. Only when they began actively feeding did they become luminous, appearing as quasars and energetic galactic centers. In this way, silence was not the end of their story. It was the beginning. It is tempting to think of explosions as the most powerful events in the universe. But gravity's greatest victories are often the quietest. When gravity wins completely, there is no energy left to escape. Nothing shouts, nothing spreads outward, everything goes inward. This is the defining character of a black hole, not violence, but inevitability, not chaos, but convergence. The first black holes embodied this perfectly. They formed not because the universe was turbulent, but because it was orderly, because mass accumulated where physics allowed it, because no force remained capable of resistance. As you lie still now, surrounded by a world shaped by countless ancient explosions, it is worth remembering that some of the most important events in cosmic history happened without spectacle. No light reached out to mark them. No shockwave announced their arrival. The universe simply changed shape, and that change would echo for billions of years. As we continue this quiet journey, another question emerges naturally from this silence. If the first black holes formed without explosions and without drawing attention to themselves, how large were they at birth, and how did they begin their long growth into the giants we observe today? That question draws us forward gently into the scale of the first black holes and the surprising modesty of their beginnings. Part 9. How large was the universe's first black hole? Compared to the supermassive black holes we see today, the first ones were modest, perhaps tens to hundreds of solar masses. Yet in the early universe, this was enough. Surrounded by dense gas and abundant matter, even a small black hole could grow rapidly. Size in this environment was only the beginning. When we imagine black holes, our minds often leap to the giants, millions or billions of times the mass of the sun, anchoring the centers of galaxies. But the universe did not begin with such monsters. It began with seeds. The first black holes were born from the collapse of the earliest massive stars. Their masses reflected the stars that created them. In many cases, these newborn black holes weighed between 10 and a few hundred solar masses. By modern standards, they would be classified as stellar mass black holes. And yet, in the early universe, they were anything but insignificant. Context matters in cosmology. A mass that seems small today could be dominant billions of years ago. The early universe was denser, richer in raw material, and far less structured. Gravity's influence was amplified by proximity. Everything was closer together. A black hole of 100 solar masses placed into that environment was a powerful object. Its gravitational pull extended far beyond its event horizon. Gas drifting nearby felt that pull and began to curve inward. As matter fell toward the black hole, it gained speed, heating through friction and compression. Even before crossing the horizon, infalling gas released energy. This energy made black holes visible, not directly, but through their effect on their surroundings. But at birth, these black holes were not luminous. They emerged quietly, embedded within dense gas clouds and dark matter halos. Their initial mass did not immediately set them apart from their environment. What mattered was not how large they were, but where they were. The first black holes formed in the deepest gravitational wells of the cosmic web. These wells were already gathering matter long before the black hole existed. When collapse produced a black hole, it inherited an environment primed for growth. In other words, the universe had already prepared their feeding grounds. Gas continued to flow inward along filaments, just as it had fed the stars before collapse. The black hole simply replaced the star as the central sink. Where fusion once resisted gravity, nothing now stood in the way. Accretion began almost immediately. Matter spiraled inward, forming an accretion disk around the black hole. This disk acted like a brake, converting gravitational energy into heat and radiation. The hotter the disk became, the more light it emitted, particularly in high-energy wavelengths. Even a relatively small black hole could shine brightly in this way. But luminosity does not necessarily limit growth. In modern galaxies, radiation from accreting black holes can push gas away, regulating how fast the black hole grows. In the early universe, this feedback was less effective. Gas was abundant, density was high, cooling was inefficient, allowing inflows to persist even in the presence of strong radiation. The black hole's surroundings could replenish material faster than radiation could expel it. As a result, growth rates could be extraordinary. A black hole doubling its mass repeatedly over tens of millions of years can grow dramatically. Starting from a few tens of solar masses, such a black hole could reach thousands or even millions of solar masses within a relatively short cosmic time. This possibility is crucial to understanding what we observe today. When astronomers look deep into the universe, they find quasars, bright energetic objects powered by accreting supermassive black holes, already in place less than 1 billion years after the Big Bang. Some of these black holes exceed 1 billion solar masses. At first glance, this seems impossible. How could a black hole grow so large so quickly, starting from a stellar remnant? The answer may lie in the favorable conditions of the early universe and in the initial mass of the first black holes. Even modest beginnings, given the right environment, can lead to extraordinary outcomes. There is also the possibility that some first black holes were larger from birth. In addition to stellar collapse, some models suggest that under specific conditions, massive gas clouds could collapse directly into black holes without forming stars at all. These direct collapse black holes could have initial masses of tens of thousands of solar masses or more. If such objects formed, they would have had an even greater head start. Whether formed from stars or direct collapse, the key idea remains the same. Early black holes did not need to be enormous to matter. They needed time, fuel, and gravity. And they had all three. It is also important to remember that black hole growth is not smooth or guaranteed. Accretion can be episodic. Feedback can slow it. Mergers between black holes can add mass suddenly. The early universe was dynamic and chaotic, full of competing processes. But chaos often favors extremes. Dense regions became denser. Massive objects grew more massive. Small advantages were amplified over time. This is a recurring theme in cosmic evolution. The first black holes were part of this amplification. As dark matter, halos merged. The black holes within them could also merge. Binary black holes formed. Gravitational waves rippled outward as they coalesced. Each merger added mass and spin, pushing black holes further along their growth paths. Even without accretion, mergers alone could increase black hole mass significantly. Combined with accretion, they became a powerful growth mechanism. From a distance, the universe slowly transitioned. What began as a collection of modest black holes embedded in gas clouds evolved into a cosmos dotted with luminous quasars and massive galactic centers. The first black holes were not erased by time, they were transformed. Their initial size determined their starting point, but not their destiny. In some sense, the modesty of the first black holes is reassuring. It tells us that the universe did not require exotic beginnings to produce its most extreme objects. It relied on familiar physics, applied patiently and repeatedly. Gravity gathered matter, collapse formed black holes, accretion and mergers did the rest. As you rest now, consider how scale changes meaning depending on context. 100 solar masses may feel small compared to a galaxy, but in the early universe, it was a gravitational anchor. It was enough to bend trajectories, redirect flows, and alter futures. The first black holes did not dominate the universe by size alone. They dominated by position and opportunity. They sat at the crossroads of matter and motion, quietly accumulating influence. And from these beginnings, something remarkable followed. If a black hole of modest size could grow so effectively in the early universe, what mechanisms allowed that growth to continue, unchecked, for millions of years? That question carries us gently forward into the story of how the first black holes began feeding, how gravity, gas, and time worked together to transform seeds into giants. Part 10. How did early black holes begin to grow? Once formed, the first black holes found themselves immersed in rich cosmic fuel. Gas spiraled inward, heating and glowing before vanishing beyond the horizon. With little competition and few disruptive forces, these early black holes fed steadily, transforming from stellar remnants into the seeds of far larger structures. A black hole, once born, is never truly alone. It exists within an environment shaped by the same gravity that created it. In the early universe, that environment was unusually generous. Matter was abundant, distances were small, and the cosmic web funneled gas efficiently toward the deepest gravitational wells. For a newborn black hole, this meant opportunity. Unlike stars, black holes have no internal pressure, no fusion-driven balance to maintain. Nothing inside pushes outward. There is no surface to resist infalling matter. Once gas drifts close enough, gravity does the rest. But matter does not fall straight in. Even the smallest sideways motion becomes important near a black hole. As gas approaches, it begins to orbit, forming a swirling accretion disk. Within this disk, particles collide, rub past one another, and lose energy through friction. That lost energy emerges as heat and radiation. This process is remarkably efficient. A black hole, converting gravitational energy into radiation through accretion, can outshine entire galaxies. Yet in the early universe, this brilliance did not necessarily halt growth. Radiation escaped, but gas kept coming. One reason was geometry. In the dense early cosmos, gas often flowed along narrow filaments, guided by dark matter. These streams delivered matter directly toward black holes, replenishing their surroundings even as radiation tried to push material away. Accretion became directional, persistent, and difficult to interrupt. Another reason was timing. The first black holes formed before the universe was crowded with stars, winds, and explosions. There were few competing sources of energy nearby. No stellar feedback heated or dispersed gas on large scales. Black holes faced little resistance from their environment. They fed in relative peace. Accretion rates during this era may have approached or even exceeded what physicists call the Eddington limit, the theoretical maximum rate at which radiation pressure balances gravity. In modern galaxies, this limit often regulates black hole growth. In the early universe, conditions may have allowed black holes to grow faster, at least temporarily. This rapid feeding did not require exotic physics. It relied on density, proximity, and patience. As gas fell inward, it carried angular momentum, shaping the accretion disk and influencing the black hole's spin. Over time, black holes spun faster, altering how efficiently they converted infalling mass into energy. Faster spin allowed matter to orbit closer before crossing the horizon, increasing radiative output. Even so, growth continued. It is important to remember that black holes do not need to be efficient eaters to grow large. They need consistency. A steady trickle of mass over millions of years adds up. In the early universe, millions of years passed quickly. As dark matter halos merged, black holes were carried along. When halos collided, their gas reservoirs combined. Accretion flared. When black holes encountered one another, they formed binaries and eventually merged, adding their masses together. These mergers were silent in light, but loud in gravity. Gravitational waves rippled outward, carrying energy away and allowing the black holes to settle into a single, more massive object. Each merger represented a sudden step in growth, independent of accretion. Together, accretion and mergers worked hand in hand. Some black holes grew mainly by feeding, others grew mainly by merging. Most experienced a combination of both. The early universe provided all pathways simultaneously. What made this era unique was the lack of regulation. In later cosmic history, black hole growth becomes self-limiting. Powerful jets and radiation heat surrounding gas, preventing further inflow. Galaxies develop stable structures that limit how much material reaches their centers. Growth slows. But early on, none of this was established. Galaxies themselves were still forming. Their structures were loose, irregular, and turbulent. Gas could flow inward without encountering organized resistance. Black holes benefited from this chaos. In a sense, early growth was accidental. Black holes did not need to compete with complex ecosystems of stars and feedback loops. They simply sat where matter naturally flowed and waited. This waiting is a key idea. Black holes do not hunt. They do not pull matter from afar with intent. They grow because matter wanders too close. In the early universe, wandering was common. Even modest black holes could therefore experience long periods of uninterrupted growth. A black hole starting at 50 solar masses could, under favorable conditions, reach thousands within a few tens of millions of years. Over hundreds of millions of years, the growth could be staggering. This is why the early universe appears to have produced massive black holes so quickly. It was not because black holes were special, it was because the universe itself was unusually cooperative. The environment did the work. As black holes grew, their influence expanded. Their gravity affected gas dynamics on larger scales. Their radiation began to heat surrounding regions, In some cases, this feedback eventually slowed growth. In others, it reshaped the host galaxy. The relationship between black holes and galaxies began here. At first, black holes were passengers carried along by cosmic flows. Over time, they became drivers, shaping the evolution of the structures around them. The balance between feeding and feedback emerged gradually, but in the earliest stages, feeding dominated. There is something almost gentle about this process. Despite the extreme physics involved, growth unfolded slowly, governed by steady inflow rather than catastrophic events. Black holes expanded not through sudden leaps, but through accumulation. Gravity, once again, proved to be patient. As you breathe now, each breath adding quietly to the moment before it, you are experiencing the same principle. Change does not always announce itself. Sometimes it arrives through repetition. The first black holes grew this way, one particle at a time, one orbit at a time, one merger at a time. And as they grew, they crossed thresholds of influence. At certain masses, black holes could anchor entire galaxies. At larger masses, they could regulate star formation. At still larger scales, they became the luminous engines we observe as quasars. All of this began with feeding, with gas drifting inward, with friction turning motion into light, with gravity converting mass into curvature. Once the universe discovered this pathway, it never abandoned it. Black hole growth remains one of the central processes shaping cosmic evolution. The first black holes were not anomalies. They were prototypes. And yet, even as they grew, another mystery lingered. If early black holes fed so effectively, could some of them have formed already massive, skipping the stellar stage entirely? That question draws us gently onward, into the possibility of black holes born not from stars, but directly from collapsing gas itself. Part 11. Could some black holes have formed without stars at all? Some theories suggest an even quieter origin. In regions where gas collapsed directly without ever igniting into stars, gravity may have skipped the stellar phase entirely. These direct collapse black holes could have been born already massive, forming not from death, but from overwhelming accumulation. To understand this idea, it helps to release the assumption that stars must come first. In most of the universe we see today, stars are the natural intermediaries between gas and black holes. Gas collapses, ignites, shines, and eventually dies. But the early universe did not always follow this familiar sequence. In certain rare environments, conditions may have allowed gravity to act without interruption. These environments were defined by two crucial traits: immense amounts of gas and an inability to cool too efficiently. Cooling, paradoxically, can prevent direct collapse. When gas cools rapidly, it fragments into smaller clumps, forming stars. To bypass stars entirely, gas must stay warm enough to resist breaking apart while still being dense enough to collapse as a whole. In the early universe, this delicate balance may have existed. Consider a massive dark matter halo forming at the intersection of cosmic filaments. Gas streams pour in from multiple directions, delivering enormous amounts of material. The gravitational well deepens, density rises. But if certain wavelengths of radiation suppress the formation of molecular hydrogen, the primary coolant in primordial gas, the cloud cannot fragment easily. Without molecular hydrogen, the gas remains relatively warm. Warm gas resists fragmentation. Instead of breaking into many stellar cores, it continues collapsing inward as a single massive structure. Gravity pulls from all sides. Rotation redistributes material, but does not stop the inflow. The cloud grows heavier and more compact. At no point does fusion ignite. Temperatures rise, but not in the right way. Pressure builds, but it is not balanced by nuclear energy. The gas becomes supported briefly by thermal pressure, then radiation pressure, but gravity continues to win as mass accumulates. Eventually, the collapsing cloud reaches a critical point. Its central region becomes so dense and massive that general relativity takes over. Space-time curves inward sharply. An event horizon forms. A black hole is born. No star ever existed. This is the essence of the direct collapse black hole scenario. It is not violent. It does not require explosions or deaths. It is gravity doing what it does best, uninterrupted on a grand scale. The black holes formed this way would be very different from stellar remnants. Instead of tens of solar masses, they might begin life with thousands, tens of thousands, or even hundreds of thousands of solar masses. These would not be seeds, they would be saplings. Such an origin helps explain one of the most puzzling observations in cosmology: the presence of extremely massive black holes very early in the universe's history. Some quasars observed less than 1 billion years after the Big Bang appear to host black holes with masses exceeding 1 billion suns. Growing that large from a small stellar remnant is challenging, even under ideal conditions. But starting from a much larger initial mass makes the problem far easier. Direct collapse black holes provide a possible shortcut. Yet this pathway is not easy to achieve. It requires precise conditions: too much cooling and stars form, too little mass and collapse stalls, too much angular momentum, and the gas forms a disk instead of collapsing inward. The universe did not offer these conditions everywhere. They were rare. But rarity is not the same as impossibility. The early universe was vast. Even unlikely configurations could occur multiple times across cosmic scales. Computer simulations suggest that direct collapse conditions may have arisen in specific halos exposed to strong ultraviolet radiation from nearby star-forming regions. This radiation could suppress molecular hydrogen formation, keeping gas warm and cohesive. In these special neighborhoods, stars formed nearby, but not locally. Their light shaped the chemistry of neighboring gas clouds, preventing fragmentation and enabling direct collapse. In a quiet irony, stars may have indirectly helped create black holes that skipped being stars themselves. Once a direct collapse black hole formed, its growth prospects were excellent. It already possessed significant mass. Its gravitational pull was strong from the beginning. Gas inflows could continue, feeding it efficiently. These black holes would rapidly become dominant objects in their host halos, influencing galaxy formation from the earliest stages. They would also merge with other black holes, both stellar and direct collapse varieties, further accelerating growth. From the outside, distinguishing a direct collapse black hole from one grown from stellar remnants is difficult. Both obey the same physics. Both interact with their environments similarly once formed. But their origins matter. They tell us that the universe may have more than one pathway to darkness, that black holes are not merely the endpoints of stellar life, but can also be primary structures in their own right. This idea challenges intuition. We are accustomed to thinking of complexity building, step by step. Gas becomes stars, stars become black holes, but gravity does not require steps. It requires only mass and time. Given enough of both, it can bypass intermediate stages entirely. There is something deeply quiet about this possibility. A black hole forming without light, without fusion, without death. No star shines, no explosion marks the moment. The universe simply folds inward, and a horizon appears. Distance, nothing changes. Yet, something irreversible has occurred. This reinforces a theme that runs throughout cosmic history. The most consequential events are not always the loudest. The universe is shaped as much by what does not happen as by what does, by collapses without explosions, by formations without light, by gravity acting alone. Direct collapse black holes, if they exist, are monuments to that principle. They also remind us that our understanding of the early universe is incomplete. These objects remain theoretical, supported by simulations and indirect evidence, but not yet observed directly. Future telescopes may provide clues: the environments of early quasars, the mass distributions of ancient black holes, the signatures of primordial gas dynamics. Each observation will help refine the story. For now, the possibility remains open. Some of the universe's first black holes may not have been born from dying stars at all. They may have emerged fully formed from collapsing gas, ancient and massive from their very first moment. If so, they would have influenced cosmic evolution profoundly, acting as anchors around which galaxies assembled. And that leads naturally to the next quiet question. Whether born from stars or from direct collapse, how did these early black holes begin shaping the first galaxies around them? That question carries us forward, gently, into the relationship between black holes and the birth of galaxies themselves. Part 12. How did black holes shape the first galaxies? Even in their infancy, black holes influenced their surroundings. As matter fell inward, energy was released, heating nearby gas and regulating star formation. In this way, black holes were not just consumers, they were architects, quietly shaping the growth of the first galaxies from their hidden centers. When the first galaxies began to assemble, they were fragile things. They were not yet the graceful spirals or smooth ellipses we see today. Instead, they were loose gatherings of gas and dark matter, still forming, still adjusting to gravity's long pull. In these young systems, even small influences could have lasting effects. Black holes provided one of those influences. At the centers of the densest regions, black holes sat quietly, their presence defined not by light, but by gravity. Gas flowed toward them along the filaments of the cosmic web, just as it flowed toward forming stars. But unlike stars, black holes did not simply consume fuel and shine steadily. Their feeding altered their environment in complex ways. As gas spiraled inward, it heated dramatically. Friction within accretion disks converted motion into energy, releasing radiation across the electromagnetic spectrum. This energy did not remain confined to the black hole. It poured outward, bathing nearby gas in heat and light. This heating mattered. Warm gas behaves differently from cold gas. Cold gas collapses easily, forming new stars. Warm gas resists collapse. By heating their surroundings, black holes could slow or suppress star formation in their immediate vicinity. This effect, known as feedback, acted as a regulating mechanism. In the earliest galaxies, regulation was crucial. Without it, gas could collapse too quickly, forming stars at unsustainable rates. Rapid star formation consumes gas, triggers explosions, and disrupts galactic structure. Black hole feedback helped prevent this runaway behavior by moderating the pace of collapse. In this sense, black holes acted like quiet governors. They did not stop star formation entirely. Instead, they influenced where and when it occurred. Regions closer to the black hole experienced stronger heating. Regions farther away remained cool enough to form stars. This created gradients within young galaxies, shaping their internal structure. Feedback was not always gentle. In some cases, rapidly accreting black holes launched powerful jets of particles and energy along their rotational axes. These jets could punch through surrounding gas, carving channels, and redistributing material across vast distances. Even early black holes may have produced such jets, though their environments were denser and more chaotic. Jets did not destroy galaxies, they rearranged them. By pushing gas outward in some directions and allowing inflow in others, jets and winds helped shape the morphology of early galaxies. They influenced where stars formed and where gas accumulated. Over time, these effects contributed to the diversity of galactic forms. It is important to understand that black hole influence was not instantaneous. Galaxies did not suddenly reorganize around black holes. The process unfolded over millions of years, gradually imprinting patterns that would persist. The relationship between black holes and galaxies was reciprocal. As black holes fed, they influenced their host galaxies. As galaxies evolved, they influenced black hole growth. Gas supply, mergers, and galactic dynamics all affected how much material reached the central black hole. This feedback loop tied the fate of black holes and galaxies together. Observations of the modern universe reveal a striking correlation. The mass of a galaxy's central black hole is closely related to the mass of its stellar bulge. This relationship suggests a long history of co-evolution, beginning in the earliest galaxies. The roots of that relationship lie here. In the first galaxies, black holes helped set the pace of growth. They prevented extremes. They smoothed out imbalances. They helped transform chaotic gas clouds into more stable systems. Without black holes, early galaxies might have burned themselves out too quickly, converting gas into stars before structures could settle. With black holes present, growth became more measured. This does not mean black holes were benevolent. They were indifferent. Their influence arose naturally from physics, not intention. But the result was structure. Another way black holes shaped early galaxies was through mergers. As dark matter halos merged, their galaxies merged with them. Central black holes were brought together, forming binary systems. Over time, these black holes spiraled inward and merged, releasing gravitational waves and combining their masses. Each merger reshaped the galaxy. Merging black holes stirred surrounding gas, triggered bursts of star formation, and altered galactic dynamics. The combined black hole became more massive and more influential, deepening the gravitational well at the galaxy's center. This process repeated over cosmic time, gradually building the massive black holes we see today. Even when black holes were not actively feeding, their gravity mattered. A massive object at the center of a galaxy stabilizes orbits, influences stellar motion, and anchors the system. In young galaxies, this anchoring effect helped organize motion and reduce chaos. Black holes provided a reference point in a turbulent universe. As galaxies grew, their interactions became more complex. Gas cooled, stars formed, feedback cycles intensified, but the foundational relationship between black holes and galaxies remained. It began early and persisted. From a distance, it may seem strange that something so small compared to a galaxy could have such influence. But gravity does not care about size in the way we do. It cares about mass and concentration. A black hole concentrates mass more efficiently than anything else in the universe. This concentration gives it power. Even when hidden behind gas and dust, black holes shape the evolution of their hosts. Their presence influenced flows of matter, energy, and time itself. They were silent partners in the building of cosmic architecture. As you lie still now, it may be comforting to think of galaxies as stable, ancient things. But they were once fragile, uncertain structures, finding their balance in a universe still learning how to organize itself. Black holes helped that process. They were not accidents or afterthoughts. They were integral components from the beginning, shaping galaxies even as they were shaped by them. And yet, despite their influence, black holes themselves remained mostly invisible. Their presence had to be inferred from motion, from light, bent, and energy released nearby. This invisibility raises another question. If black holes shaped the first galaxies so profoundly, what traces of those ancient interactions can we still observe today? That question leads us gently onward into the evidence left behind, faint signals from deep time that still whisper the story of the universe's first black holes. Part 13. What evidence do we see today of these ancient objects? When we look deep into space, we also look back in time. Quasars, brilliant beacons powered by feeding black holes, appear astonishingly early in cosmic history. Their existence tells us that black holes must have formed quickly, efficiently, and long before the universe was calm or mature. Light does not arrive all at once. It travels. And the farther it travels, the older the story it carries. When astronomers point their instruments toward the most distant regions of the cosmos, they are not just seeing far away, they are seeing long ago. In that ancient light, the universe preserves evidence of its earliest structures, including the first black holes. The most striking of these clues comes from quasars. Quasars are among the brightest objects in the universe. They shine with the combined light of entire galaxies, yet they originate from regions no larger than our solar system. Their power source is not stars, but accretion, matter falling into supermassive black holes at the centers of young galaxies. What makes quasars remarkable is not just their brightness, but their age. Astronomers have detected quasars that existed less than 1 billion years after the Big Bang. Some appeared when the universe was only a few 100 million years old. At that time, galaxies were still assembling, stars were still forming in great numbers, and yet, black holes with masses of hundreds of millions or even billions of suns were already in place. This should not be possible, at least not easily. If black holes began as small stellar remnants, growing only through gradual accretion, there would not have been enough time to reach such enormous sizes. The presence of early quasars forces us to reconsider how and when black holes formed. They are silent witnesses, shining across time. Beyond quasars, astronomers see other signs. When galaxies are observed at high redshift, meaning their light has been stretched by the expansion of the universe, they often show evidence of energetic central engines. These galaxies are irregular, turbulent, and gas-rich, yet many already host active black holes. The early universe was not empty of darkness, it was structured by it. Another line of evidence comes from the cosmic microwave background, the faint afterglow of the Big Bang. This radiation carries subtle imprints of how matter and energy evolved over time. Tiny variations in temperature and polarization reveal how the first structures formed and how radiation interacted with matter. Some of these patterns are influenced by early black hole activity. As black holes accreted matter and released energy, they heated surrounding gas and altered how radiation traveled through space. These effects left faint but measurable signatures in the cosmic background, offering indirect evidence of black hole growth during the universe's infancy. Gravitational waves provide another, more recent window into ancient events. When black holes merge, they send ripples through space-time, distortions that travel outward at the speed of light. Modern detectors like LIGO and Virgo have observed mergers between black holes with masses larger than typical stellar remnants. Some of these black holes may be descendants of early cosmic populations. The masses observed suggest origins in low metallicity environments, similar to conditions in the early universe. While these mergers occur much later in time, they carry information about black hole formation pathways that began billions of years ago. Even the distribution of galaxies today offers clues. The large-scale structure of the universe, the cosmic web of filaments, clusters, and voids, reflects the influence of gravity over immense timescales. At the centers of massive galaxies, supermassive black holes are nearly ubiquitous. Their presence correlates strongly with galactic properties, suggesting a long history of interaction. This correlation did not arise recently. It had to begin early. The tight relationship between black hole mass and the velocity of stars in a galaxy's bulge implies that black holes and galaxies grew together. Such coordination requires early and sustained influence, pointing back to the first generations of black holes. There is also evidence in chemical signatures. Regions influenced by early black hole activity show differences in gas composition and ionization states. By studying the spectra of distant galaxies and quasars, astronomers can infer the presence of powerful radiation sources long before stars alone could account for them. These spectral fingerprints act like time capsules, preserving conditions from the universe's youth. Even the absence of certain signals is informative. The early universe went through a phase called ionization, when neutral hydrogen was gradually ionized by the first sources of light. The timing and patchiness of this process depend on the distribution of stars and black holes. Observations suggest that black holes likely contributed to ionization alongside stars, adding to the evidence of their early presence. All of this evidence points in the same direction. Black holes did not arrive late to the cosmic story. They were present near the beginning, shaping the universe quietly but persistently. Yet it is important to remember that none of this evidence is direct. We have not seen the first black hole form. We infer its existence through consequences, through light bent, heated, delayed, and amplified by gravity. This indirectness is fitting. Black holes hide their interiors. They reveal themselves only through influence. And so their earliest history must be reconstructed the same way, by tracing how they altered the universe around them. In a sense, the universe itself is the record. Every quasar, every gravitational wave, every correlation between galaxies and their centers adds another line to the story. Together, they form a coherent picture, a cosmos where black holes emerged early, grew rapidly, and became integral to structure formation. As you rest now, it may feel strange to think that something invisible could leave such lasting marks. But much of reality works this way. Wind shapes landscapes without being seen. Time shapes lives without being touched. Black holes shape the universe without shining. The evidence we see today is not loud. It is subtle, statistical, cumulative. It requires patience to interpret and humility to accept. But it is compelling. The universe keeps its memories not in narratives, but in patterns. And those patterns tell us that long before galaxies settled into their familiar forms, long before stars like the Sun existed, black holes were already there, quiet, massive, and influential. This realization leads to a deeper reflection. If black holes were present from the beginning, if they shaped galaxies and structures so profoundly, what does that say about their role in the universe today? And more quietly still, what does it say about the universe itself, that such darkness was part of its original design? Those questions carry us gently forward toward the final reflections of our journey, where we consider why the first black hole still matters and what it teaches us about the nature of existence itself. Part 14. Why does the first black hole still matter now? Every black hole we observe today carries echoes of that first collapse. The rules that governed its birth still shape cosmic evolution. From galaxy formation to the flow of time near extreme gravity, the universe continues to follow patterns written during those earliest moments of darkness. It is easy to think of the first black hole as a relic, an ancient event sealed off from the present by billions of years. But in reality, the first black hole is not gone. It is still here, not as a single object, but as a template. Every black hole that exists today is a descendant of the same physical principles that allowed that first collapse to occur. The universe does not rewrite its rules, it refines them. When the first black hole formed, it demonstrated something profound. Gravity, given enough mass and time, can overwhelm every other force. That lesson did not fade with cosmic expansion, it became foundational. Every star that collapses today follows the same script, obeys the same thresholds, curves space-time in the same way. In this sense, the first black hole was not an exception. It was a proof. It proved that space-time could fold in on itself, that escape could become impossible, that time itself could be redirected inward. Once proven, the universe continued using this outcome wherever conditions allowed. Modern black holes, whether stellar mass objects in binary systems or supermassive giants at galactic centers, are repetitions of that first event. Each one reenacts the same physics, scaled by mass and environment. The first black hole matters because it set the precedent. It also shaped how galaxies evolved long after its formation. The relationship between black holes and galaxies did not emerge gradually over billions of years. It was present from the beginning. That early coupling established feedback mechanisms that persist to this day. When astronomers observe galaxies now, they see a consistent pattern. The growth of stars and the growth of central black holes are linked. Galaxies that grow rapidly tend to host rapidly growing black holes. Galaxies that slow down often show signs of black hole feedback, suppressing star formation. This coordination traces back to early cosmic history. The first black holes influenced the earliest galaxies, setting up feedback loops that became increasingly refined over time. Modern galaxies inherit these dynamics. They are shaped by the same balance between gravity, gas inflow, and energy release that began in the universe's youth. Even the largest structures in the universe carry this imprint. Galaxy clusters, vast assemblies of hundreds or thousands of galaxies, contain enormous reservoirs of hot gas influenced by black hole activity. Jets from supermassive black holes inject energy into this gas, preventing it from cooling too quickly. This process regulates the growth of entire clusters. That regulation depends on principles discovered by the first black hole. The flow of time itself is also shaped by these early rules. Black holes are the clearest demonstrations of general relativity in action. Near them, time slows, space curves, and paths bend. These effects are not theoretical curiosities. They are measurable, observable, and real. Modern experiments, from tracking stars near the Milky Way's central black hole to observing gravitational waves, confirm predictions born from the same physics that governed the first collapse. The first black hole was where relativity became unavoidable. Before stars and galaxies, gravity was gentle. After black holes formed, gravity entered a new regime, one where space-time could be dramatically reshaped. That regime still exists. Every time two black holes merge, space-time ripples outward, reminding the universe of that original threshold. Even our understanding of information, entropy, and the limits of knowledge is influenced by black holes. The first black hole introduced a new question into physics. What happens to information when it crosses an event horizon? This question remains unanswered. It connects gravity, quantum mechanics, and thermodynamics in ways that challenge our deepest assumptions. In this way, the first black hole is still teaching us. It continues to define the boundaries of what we can know. It sets limits on observation, causality, and prediction. It forces physicists to confront the edges of theory, where existing models strain and sometimes fail. The first black hole matters because it revealed a flaw, or perhaps a feature, in our understanding of reality. It also matters philosophically. Black holes remind us that darkness is not an absence of structure, but an expression of it. They are not voids carved into the universe. They are outcomes of its laws, as natural as stars and planets. The universe did not become broken when the first black hole formed. It became complete. From that moment on, existence included regions where return was impossible, where time behaved differently, where information was hidden. These regions are not errors, they are consequences. As you rest now, breathing quietly, time passing evenly around you, it may feel distant to think of places where time bends and futures narrow to a single direction. But those places shape the universe you inhabit. They influence how galaxies grow, how stars live, and how matter moves across cosmic scales. Even the sun's orbit around the Milky Way is influenced indirectly by the presence of the supermassive black hole at our galaxy's center, a black hole whose ancestry traces back to the earliest epochs. The first black hole matters because it connects past and present seamlessly. It reminds us that the universe has memory. Not memory in the way living beings do, but memory embedded in structure, law, and pattern. Once a rule is written into space-time, it remains. Gravity still collapses matter. Event horizons still form. Time still slows near massive objects. None of this has changed. And perhaps most quietly, the first black hole matters because it reframes our sense of scale and importance. Human history spans thousands of years. The universe has been shaping itself for billions. The first black hole formed long before life existed, yet its consequences reach into the present moment. It influences the night sky. It shapes the galaxies we observe. It defines the limits of physics we study. It is ancient, but not irrelevant. In the end, the first black hole matters because it shows us that the universe is consistent. It does not forget its own rules. It does not abandon its own experiments. What worked once continues to work now. And as we approach the final reflection of this journey, one last question rises gently into focus. If the first black hole reveals so much about the universe's nature, what does it ultimately teach us about ourselves, about our place in a cosmos where even darkness has structure and silence can shape everything? That question carries us softly toward the closing of our story, where understanding gives way to perspective and knowledge settles into quiet awe. Part 15. What does the first black hole teach us about the universe? The universe did not begin with monsters, but it allowed them to form naturally. From simplicity came complexity. From calm came collapse. The first black hole reminds us that darkness is not an interruption of the cosmos, but one of its original expressions, ancient, lawful, and deeply woven into reality itself. When we trace the universe back to its earliest moments, we do not find chaos. We find order. We find expansion governed by precise laws, matter cooling in predictable ways, and gravity, patiently amplifying the smallest imperfections. The first black hole was not an accident in this process, it was a consequence. This teaches us something essential. The universe does not distinguish between creation and destruction in the way we do. Collapse is not failure, it is transformation. When gravity overcame all resistance for the first time, the universe was not breaking down, it was exploring what its own rules allowed. The first black hole shows us that extremes arise naturally from simplicity. There were no special ingredients required, no rare substances, no violations of physics, just mass, time, and gravity acting without interruption. Given enough of these, the universe inevitably produces regions where escape is impossible. This is a quiet lesson in inevitability. Black holes often feel unsettling because they seem to erase things. Light disappears, information vanishes from view, time behaves strangely. But from the universe's perspective, nothing is being erased. Everything is being conserved, reshaped, and redistributed according to law. The darkness of a black hole is not emptiness, it is fullness compressed beyond return. The first black hole also teaches us about patience. It did not form quickly. It required hundreds of millions of years of preparation. Tiny density fluctuations had to grow, gas had to gather, stars had to form and burn. Gravity waited through every step. This patience is written into the universe itself. Change does not rush. The most dramatic outcomes often emerge from the slow accumulation of small, quiet processes. The first black hole was the result of persistence, not violence. There is also a lesson here about scale. From a human perspective, black holes feel enormous and terrifying. From the universe's perspective, they are just one outcome among many. They occupy tiny fractions of space. They influence their surroundings profoundly, yet they are rare compared to stars and galaxies. The universe allows monsters, but it does not center itself around them. This balance matters. It tells us that extremes do not dominate reality. They coexist with calm, with structure, with vast regions where nothing collapses at all. Darkness and light share the cosmos, neither overwhelming the other. The first black hole also teaches us humility about knowledge. At its heart lies a singularity, a place where our current understanding breaks down. Physics, as we know it, cannot fully describe what happens there. The equations diverge, predictions fail. This is not a weakness of the universe, it is a limit of our models. The first black hole marks the boundary between what we can explain and what we cannot yet reach. It reminds us that the universe is deeper than our theories, more subtle than our language, and not obligated to be fully understood. And yet, even in mystery, there is structure. Event horizons obey precise mathematics. Black holes radiate in subtle ways. Their mergers produce gravitational waves that match theory with astonishing accuracy. The unknown does not negate the known. It grows out of it. The first black hole teaches us that mystery is not chaos, it is unfinished understanding. There is also a lesson about time. Black holes reveal that time is not universal. It flows differently depending on gravity. Near a black hole, time slows. At the horizon, it appears to stop from an outside perspective. Inside, it points inexorably inward. This shows us that time is not a background stage on which events happen. It is part of the universe's structure, shaped by mass and motion. The first black hole was the first place where this truth became unavoidable. Before it, gravity curved space gently. After it, space-time could fold so deeply that future and direction merged. This changed the universe's possibilities forever. The first black hole also teaches us about origins. We often search for beginnings that are clean and bright. First light, first stars, first galaxies. But the universe's history includes darkness from the start, not as absence, but as potential. The first black hole was not a deviation from creation, it was part of it. This reframes how we think about darkness itself. Darkness is not merely what happens when light is gone, it is what happens when gravity completes its work. It is structure beyond visibility. In this way, black holes are not symbols of destruction, they are symbols of completion. They show us what happens when physical laws are followed to their logical conclusion, without interruption or compromise. There is also something deeply calming in this realization. The universe is not fragile. It does not need protection from its own processes. It can create stars and destroy them, form galaxies and reshape them, open horizons and close them again through mergers. Everything that happens is allowed. The first black hole teaches us that the universe is comfortable with extremes. It does not avoid them, it integrates them. As you lie still now, perhaps feeling small beneath the night sky, this perspective can be grounding. You are part of a universe that does not rush, that does not panic, that does not judge outcomes as good or bad. It simply unfolds. The same laws that shaped the first black hole shape the matter in your body. The same gravity that bent space-time there holds you gently to the Earth now. The same patience that allowed collapse then allows stability here. Nothing about black holes is separate from the rest of reality. They are not invaders, they are expressions. The first black hole teaches us that even the most extreme phenomena arise naturally when conditions align, that nothing in the universe is arbitrary, that darkness has rules, structure, and history. And perhaps most quietly of all, it teaches us that the universe does not fear its own depth. It allows regions where light cannot return. It allows futures with only one direction. It allows mysteries that persist for billions of years. And still, stars shine, galaxies form, life emerges. The presence of black holes does not diminish the universe's beauty. It completes it. As this journey comes to rest, there is no final lesson to memorize, no conclusion to force, only a gentle perspective to carry with you. The universe began simple. It grew complex. It allowed collapse. It allowed darkness. And through it all, it remained lawful, patient, and vast. The first black hole was not the end of something bright. It was the beginning of a deeper understanding of what the universe is capable of becoming. And as you drift towards sleep, beneath a sky shaped by gravity's quiet work, you can rest knowing this. Even the deepest darkness belongs here.